Hi guys, welcome back. So we've just done a video on projectile motion and we did that using some examples that had a ball that was being kicked or thrown from the ground. So this is a little bit of a different example because this time we're not actually throwing something or kicking something from the ground. We're actually kicking it from a height or from a platform. So I've got a little diagram here just to show you what I mean, and I'm going to use this question and draw on this diagram to just show you how this is going to work. So cricket outfielder attempts to throw the cricket ball back towards the stumps. He throws the ball from a height of 1.8 meters. So I'm going to underline that there. And the other thing that I'm going to do is, because I know he's 1.8 meters above the ground, I'm going to pop this information just here. So this value for height is going to be 1.8 meters. Now, above the ground with an initial speed of 20 meters per second. So the initial velocity is going to be 20 meters per second. So that's going to be at this point here. And lastly, we've got an angle of 20 degrees to the horizontal. So that's going to be this angle here equal to 20 degrees. Now, this is going to be a little bit different from the previous example, because with the previous example, when we look at the motion of a ball with a parabola from the ground, it was actually a lot easier to work out things like the maximum height, because the maximum height was halfway through the roots of the solution. And then the other thing that we could work out really easily was the horizontal distance that had been traveled, because this literally, if we were able to find this midpoint here, if we double that length, then that's going to give us the total distance traveled. So it's actually a lot easier to work it out from the ground than it is from a platform. So rather than using the methods that we've used previously, we're going to do something a little bit different. And we're going to have a look using these parametric equations here. So these parametric equations are describing the path of the ball. What is it? A cricket ball. So it's showing the path of the cricket ball towards the stumps. So just something to keep in mind. This is the path that's being thrown, or so like the displacement, I guess. We've got some information here about the velocity, and we also have some information about the acceleration. So going through each of these, if I want to move from displacement to velocity, I'm going to have to differentiate. So in other words, I'm going to have to find, well, let's do this as the proper notation, so dy dx. And then if I want to find the acceleration, I'm going to have to derive again. So I end up with something like this. Now, if I'm going back the other way, I'm going to integrate. And then if I'm going back again, I'm going to have to integrate again. So this information is going to be helpful for us to find out what each of these values are going to be. All right, so let's start off. So what do we have to do first? Calculate the time of flight and the horizontal distance traveled. Oh, a little circle there. I wonder what that's from. Okay, so I'm going to put some information here now. So the first thing that we know is that we know that the acceleration due to gravity, okay, we know the acceleration due to gravity is always going to be 9.81 meters per second. I'm just going to write 9.8. So we could write the acceleration in terms of a vector as r dot dot t, and these two dots means that it's been derived twice. So if we wanted to go back to the position vectors like we had before, we would have to integrate it twice. And that's going to be equal to negative 9.8j, where this j here represents the unit vector for the vertical direction. And it's negative because it's going in a downward direction. So that's our acceleration. The other piece of, let's write that actually. The other pieces of information that we have is we also have the initial velocity in vector form. So let's write this as well. So we've got initial velocity. Okay, so just to show you where that initial velocity comes from. So again, this is just going to be this point here. So that's going to be our r dot naught. And you'll notice too, this has got one dot. So I would have to integrate once to get from here to here. Okay, and then the last piece of information that we are going to work out now is going to be the velocity at any time. So this idea of velocity at any time has come from, so first of all, remember we've got our distance here of 1.8 meters. That's coming off and then making that parabolic path, and then eventually it's going to hit the ground at this point here. So this initial velocity, so at this point here, our initial velocity is going to be equal to this because we've thrown the ball, but it's not been influenced by the impact of gravity just yet. Whereas here we can see that we've included this extra value because this is going to be decreasing at a rate of negative 9.8 for every second that we are going across. And that's just from the effect of gravity. Okay, so using this information now, one more thing. We also know the initial position. So I know that the height here is going to be 1.8. So I could write that the initial position is going to be equal to 1.8. And the initial position, we can use the term r to describe the position, because again, if we were to integrate this, that's going to give us the position. So that's equal to 1.8 meters. And I'm not going to write the units for this one. Okay, so what we're going to do now is we're going to integrate the velocity term, so this term here, and we're going to integrate that so that we can find an equation for this initial position. So if we consider this value here, 20 cos 20, that's actually going to be some constant value. It's not going to be an exact value, so I'm not going to write out the decimal, but I will just integrate this. Now, if we had a constant and we were integrating a constant, remember all this is going to turn into it's just going to turn into AT because I'm integrating with respect to the variable t. So this is now going to become R naught is equal to 20 cos of 20 degrees, times by t. And then that's going to be for my x component. And then we're going to do the same thing for the y component now. So if I integrate this part, I'm going to get 20 sine 20t. And then if I integrate this part here, so we're going to raise this power and then divide it by the new power. So this is going to become t squared. And then divide this by 2, we're going to get negative 0.9 t squared, and that's going to be relative to the vertical position. So now what we can do, since we know this value, we can substitute this in here so that 1.8 is equal to all of that information. Oh, no, it's not. I've just made a mistake. Sorry. This is for the initial position. So this is for any time here. Let me fix that, because I integrated this particular function here. So this is for any time. And the last little thing I need to do on the end is I just need to add some sort of constant variable. And so if I was to go back in and I was to substitute in 0, I know that I'm going to be left over with 1.8 because this is this value here. So I'm actually going to use this as my constant value. So let's rewrite that as RT is equal to all of this plus 1.8. So I'll just do that off screen. So just done a little bit of a rearranging. I've just popped that t in there, and then also I've added the 1.8 to the vertical component, not to the horizontal component, because that 1.8 meters is representing something that's a vertical distance. Okay, so let's keep going. So what was the question actually asking us? It was asking us to find the time of flight. So the time of flight, we're going to have to work out, first of all, how long this particular distance is, and we're going to also have to work out how long it takes for us to get there. Okay, so we can sort of do this as like a 2-in-1, couldn't we? So this is going to hit the ground. This is going to hit the ground when the vertical component is 0. So in other words, this bit here is going to be equal to 0. So I could write that as 0 is equal to 20t sine 20 minus 4.9 t squared plus 1.8. Now again, this bit here, 20 sine 20, that is going to be a constant value. So if you have a look, this actually starts to look like a quadratic function. So if I write each of my values, I've got A is going to be equal to this here, so negative 4.9. I've got B is equal to 20 sine 20, and then I've got C is equal to 1.8. And you can just chuck that in the polynomial solver in your calculator, or you could go through and chuck it in the quadratic formula and get your solution by hand. But I came up with 2 solutions. So the first one was negative 0.226, and then the other solution that I came up with was 1.6 224, and this is going to be seconds for this particular unit. And so if you go back to that diagram that we had drawn before, it doesn't make sense for us to have negative time. I mean, you can see why this function has come up with that negative solution, but we're going to pick this solution here, so the positive solution. So that's going to be equal to 1.6224 seconds. So now that I've got my time of flight, what I'm going to do is I'm going to find the distance using the horizontal component. So I'm just going to substitute that into the xt formula. So x of 1.6224 is going to be equal to 20 lots times by 1.6224 times by cos 20. So again, that's just come from that previous expression here. So this value here. Okay, so I've just chucked that into my calculator. I've rounded it a little bit, so I don't think this is the most accurate answer, and I got 30.07 meters. Again, because I just popped in the first 2 decimal places, so you're probably going to get a slightly different value to what I get if you pop in all the decimal places. Okay, so that is my time of flight, and this value here is the horizontal distance that we've traveled. So that's part A of that particular question. Okay, so let's go through and let's have a look. So what is part B actually asking us to do now? So calculate the maximum height reached. So if we go back to this diagram here, the maximum height is going to be at that peak there. So we could say that this is the point, this is our velocity, right? This is the point where the velocity is going to be equal to 0. So we can simply just find the velocity vector, let that equal to 0, and rearrange to solve for time. So let's go ahead and do that. Okay, so I've just cleared that screen off. So again, we're going to do this using just the vertical component. Now, keeping in mind, this is the velocity now that we're dealing with. It's not the position vectors. So we're actually going to use that slightly different formula. So if we're just looking at the vertical component of the velocity, then that's going to be equal to 20 sine 20 take away 9.8 t. And again, that's just come from this previous example here. So all I've done to get that into this form was I just differentiated it. Or you could take it from the previous one because we'd actually have it up here as well. Okay, so what we need to do then is we need to find that value when the velocity is equal to 0. So that's going to be equal to 20 sine 20 degrees minus 9.8. So if I rearrange that, I'm going to get t is equal to 20 sine 20 divided by 9.8. So the time that I'm going to get for that one is 0.698 seconds. So that's how long it's taken to get from here to here. Now, like I said in the beginning, what we did previously was we sort of just doubled that value, and that sort of gave us that total time. But in this case, you can see that it's falling for a lot longer because we've actually done it off of a platform. Okay, so that's why the maximum height reach is not actually in the middle of the time of flight. Okay, so the next thing that we're going to do, now that we've worked that out, we're going to work out where that position actually is. And again, we're doing that just for the vertical component. So see how, again, we would have had to integrate to get back to this function. So I'm going to substitute that into the formula 20t sine 20 minus 4.9 t squared plus 1.8. So I've just gone ahead and I filled that out now. I'm using that time value from before. So just to quickly summarize, this bit here is just saying when the maximum velocity is, and this bit here is saying what the height is when we reach that maximum velocity. Because keep in mind, like typically if we were just to calculate this bit, then we wouldn't include this little 1.8 bit on the end. But because we are throwing it off this platform, which is 1.8 meters high, we just have to remember to keep that part there so that we get a total height here of 4.19 meters. And that seems like a reasonable answer to me. All right, let's have a go at question C now. Okay, so the last thing that we have to do is to determine the speed and the angle at which the ball lands. So in other words, we've got to find the final velocity and we've got to find the angle at which that particular ball lands. Now, with this angle here, again, this angle is going to be slightly different. If we just had like a typical parabola like this, and we weren't throwing it off a platform, then that particular angle, oof, that's not great. That particular angle there would just be the same as this angle there because it would be a symmetrical parabola. But in this case, we can see that that's not going to be symmetrical. So again, we can't just use the same sneaky tricks that we've used previously. Okay, so I'll go through and show you how to do this. Okay, so I've just cleared that screen off and I've just written this piece of information here from part A. So we know that the ball is going to land at 1.6 seconds. And again, I'm just being a bit rough with this, so this is probably not going to match whatever the answer is in the back of the textbook. But let's just go through. So we need to know the velocity. So let's write that velocity function again. So r dot t is going to be equal to 20 cos 20 I. Well, that's rude. Plus 20 sine 20 minus 9.8 t j. So again, that's just come from our previous question. So now all we're going to do is we're just going to substitute in that final angle. So that's going to be equal, that final time. So 20 cos 20 degrees I plus 20 sine 20 minus 9.8 times by 1.6. I'm just going to pop this in my calculator and come back. All right, so now we've got this particular value here. What I want to do is I want to convert it into a form that's actually going to be useful to me. So I'm going to use that formula r is equal to the square root of x squared plus y squared, because remember this is just going to be our x component and this is just going to be our y component. So if we want to find the velocity vector at that point in time, this is the formula we'll use. So we'll substitute it into there. So we're going to get r is equal to the square root of 18.79 squared plus negative 8.84 squared. And again, when I put this in my calculator, I'm going to be really careful to make sure I put the brackets around the negative. So I'll come back with that solution. Okay, so I've just drawn this little diagram here so that you can see now. So this was my initial velocity here, and then this is the path that's traveled. So my position vector is going to be 18.79i minus 8.84j. So that's coming down and finishing off in this direction here. So the length of this particular line here is equivalent to the velocity, and so I've just found that using that Pythagoras' theorem rearranged formula, and that value was equal to 20.77 meters per second. All right, so the last thing that I think we need to determine, I think was the angle, was it? Yes, so we need to determine the angle at which the ball lands. So let's go ahead and have a go at that. So to do that, let's use our tan function, so inverse tan, and again, we're going to do this using the velocity. Okay, so that's going to be the derivative, not the derivative, it's going to be y dot over x dot, because keeping in mind, we're talking about the velocity here, so we need to be making sure that we're using the terms for velocity. And I'm going to go ahead and write those parametric equations. All right, so now all we need to do is we just need to substitute those values in. So we found the value of that horizontal component, and we also found the value of that vertical component for the time at which the ball lands. So it was at like 1.6 or something. And so I'm just going to chuck those values into my formula now. So negative 8.84 over 18.79. And because this is going to be a negative value, we need to consider what quadrant it should be in. So using our cast circle, I know that it's either going to be in this particular quadrant here, or it's going to be in this particular quadrant here. So again, I'll just pop that in my calculator. All right, so this was my solution that the calculator gave, and that's a reasonable solution to me. Again, sorry, I just realized what I did. That should not be in those quadrants because tan is positive in those quadrants. We wanted a negative solution. So sorry, it should have been in this quadrant or this quadrant. And the solution that it's given me is negative 25.2. So that's going to be this direction. So negative 25.2 degrees. And so that is in the correct quadrant. So what I could do, I could add that to 360 degrees, and I could get it that way, but I'm happy because it's within that domain of negative 180 to 180, so I'm not too fussed that it's not whatever it would be. So I think 360 take away 25. Well, 360 take away 20 is going to be 340. Take away 5 is going to be 235. So that's going to be 234.2 degrees. So again, it's not necessary, but just so that you can see that if I was going around that way, it'd be 234.2 degrees going, 0.8, sorry, degrees going around in the opposite direction. Okay, so that is how we find the angle, and that is how we find the final velocity. Now the last question, show that the ball travels in a parabolic path. We can just do this using something like Desmos or your graphics calculator. So I'll just show you what I've done on Desmos. Hold on. Just going to pause this 1 second. Sorry about that. I didn't want to show you my emails, but all I did was I plotted in these functions using an extra parameter here, t, and then to get this position function, I put that in there. And so then it showed me that yes, indeed, this was a parabolic path. Oh, I forgot one thing, and I forgot to add the 1.8 on the end there. Okay, so I hope that gives you an idea. So that is a parabolic curve. So I hope that gives you a bit of a better idea about how to find projectile motion of formulas that are from a platform rather than from the ground. All right, have a good day. Bye, guys.